Okay, today we'll be working on the central limit theorem. It has three parts. We are going to work on each part. We are going to understand every little detail of the central limit theorem. So central limit theorem part one, this is the central limit theorem for the sample means with the sample size n is greater than or equal to 30. One thing that you need to know here when we talk about the central limit theorem is this. For example, you have a population. Suppose we have population. You can also add this to your note catcher. Okay, we have the population. And from this population, we'll be taking samples. We'll be taking samples, not just one or two. We'll be taking many samples. Okay, say for example, this is first sample. Suppose that is the second sample. This is the third sample. Say, for example, that is S1 first sample, S2 second sample, S3 second sample, a third sample, and we'll take many samples, as many samples as possible, maybe 100 of samples. Suppose this is the nth sample. N can be any number. It can be 50 samples, it can be 70 samples, it can be 90 samples. So from the population, we are taking the samples. Okay, that is the population. From here, we are taking the samples. Now, what we are going to do is after we have the samples, we are going to find the mean of each sample. We are going to find the mean of each sample. For example, the mean of first one is x1 bar. Mean of second one is x2 bar. Mean of third one is x3 bar. And the mean of the last one, the nth sample, is xn bar. If it is a 50th sample, this is the 50th mean. If it is the 20th sample, that is the 20th mean. Then what we'll do is we'll draw the distribution for these samples. We'll draw this distribution for these samples, meaning along the x-axis, we'll have those x bar along the x-axis, and we draw the distribution. And we are going to talk about this sampling distribution. So in central limit theorem, we are going to discuss about the nature of this distribution. We'll be talking about nature of sampling distribution. Nature of sampling distribution. When I say nature, I'm talking about whether the sampling distribution of the sample means, okay, sampling distribution of the sample mean, whether this is the normal distribution, is skewed to the left, is skewed to the right. What type of distribution is this? We are going to talk about that. So in the first part, let's see what is going on. If a random sample of size n greater than or equal to 30. So from here, when you draw these samples, S1 up to Sn, when you draw the samples, suppose the size of the sample is greater than 30. That is the key there. Okay, sample of size greater than or equal to 30. So in each sample, if you count how many elements are there, you have 30 or more. Okay, 30 or more are drawn from any population. Another keyword. When I say any population, this population can be a uniform distribution, it can be skewed, it can be normal, it can be any. So this is my population. See, this is my population. It does not look like normal. Okay, any population, we have x along the x-axis, the variable, random variable along the x-axis. Standard deviation is suppose sigma. So what we are doing here is when you have any population, and from this population, you are drawing the sample of size 30 or more. So each sample has the size 30 or more. That is something you need to know. So from any population, you are drawing the sample with the size 30 or more. Then what happened is, say the mean for the population is mu. Mean for the population is mu. Standard deviation for the population is sigma. Then this sampling distribution, if we calculate the mean of each of these and then draw the distribution, this distribution will be approximately normal distribution. That is approximately normal distribution. This is approximately normal distribution. So that is the key idea in the first part of the central limit theorem. One more time, let's revisit this. So you have a population, okay? You have a population with a mean mu and standard deviation sigma. This population is any population. When I say any population, the distribution can be of any type. It can be uniform distribution, it can be normal distribution, it can be skewed distribution, it can be any. From a population of any type, you draw a sample of size 30 or more, then you draw the sampling distribution of the mean. Okay, you have mean along the x-axis and you draw the distribution. This distribution will be approximately normal. That is the statement of the first part of the central limit theorem. Okay, that is your central limit theorem part 1. So here is the example based on the first part of the central limit theorem. Let's find out what is given and what we are asked to do. The average amount of red meat a person consumes each year is 196 pounds with a standard deviation of 22 pounds. So that is the information about the general population. On the average, the amount of red meat consumed by a person is 196 with a standard deviation of 22 pounds. So you can mark that or you can annotate there in your note catcher. So this is your mean. Okay, population mean 196 and the standard deviation is 22. That's the population. You have the population with the mean 196, standard deviation 22. So from there, you draw a sample of size 50. That is the size of the sample. This is your N. You draw the sample of size 50. Okay, 50 individual is randomly selected. We have to find the probability that mean of the sample will be less than 200 pounds. So what you have to find is, you have to find, we have to find the probability that the mean of the sample will be less than 200 pounds. Probability that mean of the sample, X bar, is less than 200 pounds. What is the probability? We have to find that probability. Okay. This is quite tricky. You'll be getting some formulas here as we work on this problem. So you have to be very careful when you take the notes. So you have the population. So let's see what is given there for the population. Okay, here you have mean, that is the population mean when you use sigma. I mean mu, that is your population mean. Mean equal to 196. Okay, standard deviation equal to 22. And the size of the sample here, n equal to 22. You have to be very careful here when you work on this. So what they have given, if you look at it carefully, hold on, I just wrote something wrong there. I don't know whether you have noticed that or not. Size is 50, sample size is 50. Here is that, n equal to 50. So here you have the population mean given, population standard deviation given, sample size is 50. So what we know from the central limit theorem is when the size of the sample is greater than 30, the sampling distribution of the sample mean will be normal. So that is what we know from central limit theorem. So we are going to write that. From central limit theorem, I'm writing CLT for central limit theorem, the sampling distribution of sample means is normal. That is what we know from the central limit theorem. So if along the x-axis here in this graph, if along the x-axis here we have the sample mean, this distribution is normal. Now in the normal distribution, if you want to find the probability, now the important thing is here, if you want to find the probability in normal distribution, we need to know for this distribution, for the sampling distribution of sample means, we need to know what is the mean and what is the standard deviation. So your mean will be here in the middle. You know that the mean is in the middle. This is your mean. And for the sampling distribution, we write the mean like this. Mean with the X bar at the bottom like this, or mean with the subscript X bar. This is the mean of the sample means. Okay. So this one, remember this is very important. The mean of the sampling distribution is always equal to the population mean. This is a formula. Mean of the sample mean is always equal to the population mean. And if you look at the population mean, it is 196. So this is equal to 196. That is something you need to know. Because in order to find the probability, we need the mean and we also need the standard deviation. We have the standard deviation for the population. We don't have the standard deviation for the sampling distribution. So the standard deviation for the sampling distribution, we write like this. Standard deviation. That is equal to the population standard deviation divided by the square root of the sample size. This is the formula that you need to note. Okay, the standard deviation of the sampling distribution is equal to population standard deviation divided by the square root of n. This is the formula. So if you look at the population standard deviation here, the population standard deviation is 22 divided by the square root of the sample size. Our sample size is 50. Square root of 50. So this is equal to, if you use your calculator to divide this, 22 divided by square root of 50, you should get 3.113. I hope you got that. Okay. Is that right? Oh, 3.111 and then 3. That's right. Very good. Okay, 3.1113. So these two information, this is the mean for this one. Mean, which is 196, is here in the middle. And then the standard deviation is this. Now, if you look at the question, we are asked to find the probability that the mean of the sample will be less than 200 pounds. So along the x-axis, you have the mean. This one, the mean of the means, or mean for the sampling distribution, we saw that it's 196. 196 is here. But in the question, we are looking for 200. So 200 should be somewhere there. So suppose this value is 200. We have to find the probability that the X bar is less than 200. Less than means to the left. So we want this value. Okay, we want this value. We want that value. So if I want to calculate this probability is equal to the area under the curve from negative infinity up to 200. So I can write like this. So probability that X bar is less than 200 is equal to, in our calculator, we use normal CDF, if you remember. Normal CDF, the lower boundary for the area is negative infinity, which is written as negative E99 in our calculator. Upper boundary is 200. Mean for the sampling distribution, which is here, that is 196. And standard deviation for this distribution, we have calculated here, it is 3.1113. So if we perform this calculation in our calculator, okay, normal CDF in our calculator, you should get the result, which is 0.9007. Make sure you check that in your calculator. So that is the probability that the mean of the sample will be less than 200 pounds. Okay, part 2 of the central limit theorem. Now here you need to understand the theorem first. What is there in the theorem? If a random sample of any size, now in this case, these samples are of any size. So this is what it is. Let me draw here. We have the population. Okay, this is our population. From here, we are taking the samples S1, S2, S3, all the way to any sample Sn. Okay, we are taking these samples, but in this case, the size of the sample is any. In the first case, the population was any, but here sample of size any. You can take 10 sample with size 10 or 5 or 4 or maybe 12 or maybe 30 or even more than 30, any. Okay, if a sample of any size n are drawn from a population that is normally distributed. Now, in this case, the population is normally distributed. Population that is normally distributed. In the first part, population was any, but here the population is normal. So this population is normal. Or here, this is your population, which is normal. You have the normally distributed population with the mean mu and standard deviation sigma. From here, you are taking the samples of any size n. Okay. And once you have these samples from here, you are calculating the sample mean x1 bar, x2 bar, x3 bar, all the way up to xn bar. And you draw the distribution for these random variable. And when you draw the distribution for these random variable, the sample means, what happened is the sampling distribution of the sample mean is also normal. See, the sampling distribution of the sample mean is also normal. So if you plot the sample means along the x-axis and draw the curve, you'll see that this distribution is also normal. With the mean, you can see here, mean of the sampling distribution is equal to mean of the population mu, whereas the standard deviation of the sampling distribution is equal to population standard deviation divided by the square root of n. So that is the definition of the second part of the central limit. So here is an example on the second part of the central limit theorem. We are going to read the problem first. We are going to understand that and we'll solve it. Let's find out. The height of women are normally distributed with the mean of 63.6, that is your mean. The mean of 63.6, that is your mean mu. And standard deviation of 2.5 inch. This is only inch. Okay, then if 10 women are randomly selected, that is your sample size. If 10 women are randomly selected, we have to find the probability. Here is our question. Find the probability that they have the mean height more than 63 inches. So we have to find the probability that their mean means x bar, is greater than 63. We have to find what is that equal to. That's your question. So let's write the information that we have. What they have given is the population mean is 63.6. Here, population mean is 63.6. Population standard deviation is 2.5. Population standard deviation 2.5. And sample size is a small sample size 10. You can see here, if the sample size is 10, if it is less than 30, we don't know whether the sampling distribution is normal or not. For the sampling distribution to be normal, the population must be normal. So let's read the question again. The height of the women are normally distributed. See, they said that the population is normal. So what we know from the second part of the central limit theorem is, if the population is normally distributed, then the sampling distribution is also normal. So if I have the x bar along the x-axis, this is also normal from central limit theorem. So we write from central limit theorem, the sampling distribution, make sure you write this, the sampling distribution of, along the x-axis, we are plotting the mean of sample means then, of sample means is normal. That is what we know from central limit theorem. Now, once we have the normally distributed random variable x bar here, we need the mean in the middle. We need the mean, but this is the mean of the sampling distribution, which we write x bar. So that is this one. Mean of the sampling distribution is equal to population mean. And the population mean is 63.6. So this is equal to 63.6. Also, for this distribution here, which is normal, as we know from the central limit theorem, we also need the standard deviation for this. The standard deviation of the sampling distribution, which is written as sigma sub x bar, is equal to population standard deviation divided by the square root of n. Population standard deviation is 2.5. Hold on. One important thing here. In your question, in your note catcher, please check this. I totally forgot to mention that earlier. This should be 25, not 2.5. This is 25. Please make that correction. I'm sorry. That should be 25. Okay. The population standard deviation is 25, not 2.5. Change that in your note catcher also. So this one, it is 25 divided by the square root of, my sample size is 10. Now you can perform this calculation in your calculator. 25 divided by the square root of 10. If you do 25 divided by square root of 10, you should get 0.7906. 0.7906. That is the standard deviation for this one. So once we know the mean and the standard deviation, you can easily find this probability. So what we need to do is, let's find out what is there. We have to find the probability that the mean is greater than 63.
Hello.
So,
Sorry.
okay, we are taking back 2.5 for that. So if we take 2.5 here, that should be 0.7906. So what we did here, the probability that x is greater than 63, 63 is here, greater than is to the right. So that is equal to normal CDF, 63 is the lower limit, infinity is the upper limit, mean is 63.6, standard deviation is 0.7906. So what I want you to do is type this in your calculator and find the probability. That's right. The probability should be, after we perform this calculation, it should be 0. Let me write that. It should be 0.7760. So probability that the average height of the woman is greater than 63 will be 0.7760. So this is the example on the second part of the central limit theorem. Okay, here is the third part of the theorem, third part of the central limit theorem. This is not on mean now, this is on proportion now. Let's read the problem first. The proportion of a random sample has a sampling distribution whose shape can be approximately normal if, so there is a condition here, if n times p is greater than or equal to 10, and n times 1 minus p, sometimes we write that as q, which you know from the binomial distribution, is greater than or equal to 10. So when I say a proportion, it is like a percentage. For example, here is the population. Okay, here is the population. Suppose the proportion of the population from this population, I'm talking about this group, the proportion of the population who has master degree, okay, who has master degree is suppose 48%. If I say that, then the value of P will be 0.48. That is a 48%. That's your proportion. If I say the proportion of the population with master degree is 48%, then the value of P is 0.48. So if your P is 0.48 for this group here, the value of Q will be 1 minus 0.48, which is 0.52. So you have a population like that. Then from there, you are taking the samples. For the first sample of size n, there is a second sample of size n, third sample of size n. Then you calculate the proportion. Now the proportion of the sample is p hat. This p hat is the proportion of the sample. Now we look at the proportion of the population who has master degree here. That's your p hat. Proportion of the population or of the sample who has master degree, p hat. Proportion of the sample who has master degree, p hat. We calculate all this p hat and we draw the distribution. The distribution of these p hat, okay, distribution of these p hat will be normal if these two conditions are true. If n times p is greater than or equal to 10 and n times 1 minus p, or you can also say n minus q, is greater than 10. If these two conditions are true, then the sampling proportion, okay, if you draw the distribution of this proportion, which is also called the sampling distribution of the proportion, it will be normal. With the mean, you can see, with the mean equal to the mean of the population, p, or the proportion of the population, and standard deviation given by that formula. So here, you need to note that this one is your mean. We can write like this: mean of the proportion, means of p hat, is equal to the population proportion p, and standard deviation of p hat is equal to square root of p times 1 minus p, or you can also write q, divided by the square root of n. So here, we are not looking at the sample size, or we are not looking at the population, the nature of the population. Instead, we look at these two conditions. If n times p is greater than 10 and n times q is greater than 10, then the sampling distribution of the proportion is also normal, with the mean equal to p and standard deviation equal to square root of pq over n. So that is the third part of the central limit theorem. So here is the example on the third part of the central limit theorem. Let's find out what is given here and what we are asked to do. Okay. So first we are going to read and understand this problem. Our report states that 48% of the high school graduates are interested in STEM discipline. A random sample of 90 freshmen is selected. What is the probability that less than 60% of them are interested in STEM discipline? So about the population, they said, a report states that 48% of the high school graduates, so that is everyone in the country, 48% of everyone in the country. So that's your population proportion. So 48% of the high school graduates are interested in STEM. Meaning of that is P is equal to 48% or 0.48. So Q is equal to 1 minus 0.48, which is equal to 0.52. Okay, so that is your Q and that's your P that's given to you. And here the sample size is 90. Sample of 90 freshmen, that's your sample size, is selected. What we have to do is, what is the probability that less than 60% of them are interested in STEM education or STEM discipline? So probability that the sample proportion P hat is less than 60%, less than 0.60. What is this equal to? We need to find out. So if we need to find that, first what we are going to do is we are going to write the given information here. So here your P is equal to 0.48. So your Q is 0.52. And the sample size is 90. Now we need to check whether the distribution of the proportion is normal. So if I plot the P hat, the sample proportion along the x-axis, we have to check whether this is normal or not. In order to find out whether this is normal or not, what we do is we try to check this value. We need to check n times P and n times Q. If we find n times P N is 90. So 90 times P is 0.48. If you multiply that in your calculator, 90 times 0.48 is 43.2, which is greater than 10. Okay, as we are expecting from the central limit theorem. And then N times Q is 90 times 0.52. And that is equal to, if you multiply that in your calculator, 90 times 0.452, that is 46.8, which is also greater than 10. So both conditions are true. Since both conditions are true, we see that the sampling distribution of proportion is normal. So this implies, you have to write this sentence, this implies sampling distribution of proportion is normal by central limit theorem. This is, we know this from central limit theorem, because according to the third part of the central limit theorem, if n times p is more than 10 and n times q is more than 10, then the distribution is normal. That's why we say that from the central limit theorem, this is normal. So once we know that this is normal distribution, we need the mean for the distribution. Mean for the distribution is mean of the proportion. We write means of p hat. So that is, let's write that. Mean of the proportion is equal to population proportion. If you look at the previous slide in your note catcher. So that's your p, which is 0.48. 0.48. And then the standard deviation of this distribution here is equal to square root of pq divided by n, which is equal to square root of p is 0.48, q is 0.52 divided by n. N is your sample size, which is 90. And if we type 0.48 times 0.42 divided by 90 under the square root in our calculator, you can try this. You should get 0.0527. That is the standard deviation for this distribution here. So we have the mean and the standard deviation for this distribution. Once we have the mean and the standard deviation for this distribution, we can easily find this probability. We can easily find that probability. Now, what we are looking for is, we want the probability that the p hat is less than 0.60. Is less than 0.60, 0.60 or 0.6, which is same thing. So here, if you look at the middle, this value is 0.48. This is 0.48. So 0.60 will be more than that. It will be somewhere there. That should be 0.60. So this value here is 0.60. And we want the probability that the p hat, okay, the random variable p hat is less than 0.60. When I say less than, it is to the left. So I want the probability that p hat is less than 0.60, which is equal to this shaded area. And whenever we are calculating area under the curve or the probability, we use normal CDF in our calculator. So let's write that down.
It's not in that.
Normal CDF. So normal CDF, your lower limit for the area, it is up to the negative infinity on this side. So negative E99. The upper limit for the area is 0.60. Mean, you can see here, the mean is equal to 0.48. We got the standard deviation here, which is 0.0527. 0.0527. Now, you can type this in your calculator to check the result. Please check it. It should be 0.9886. So probability that they choose STEM discipline, okay, 60% of them will choose STEM discipline is 0.9886.